the session is Matías Menni, and his title is Spaces with Decidable Reflections. Matías?
Thanks, Susan. Also, I'd like to thank the organizers for working in such peculiar circumstances. Before I start, I should say that this is based on joint work with Vincenzo Marra from Università di Milano, and also that I'd like to dedicate this to the memory of Yuri Poveda, who died recently of COVID. He was an important member of the Colombian mathematics community, and he did a lot to promote category theory in his country. Also, it was while reading his thesis that I realized that the category of NP algebras is coextensive. And he was a lot of fun, so he wouldn't have wanted us to dwell on sub-thoughts. Let's just look at something pretty. A category is called extensive. A category with finite coproducts is called extensive if the canonical functor that you see there, from a product of slices to a slice, is an equivalence for every pair of objects x and y. And I invite you to think of a category, of an extensive category, as a category of spaces. This property of coproduct is the least possible thing that you may require from a category of spaces. You have two spaces, you put them together into a coproduct, and the original spaces appear as complemented subobjects of the coproduct. So if your mind is more into topological spaces, you can see this as providing a good notion of cloping subobject. Any topos is extensive, the category of topological spaces is extensive, the category of posets is extensive, also many full subcategories of topological spaces inherit extensivity from the larger one, so compact Hausdorff spaces, stone spaces, but also non-full subcategories that are intuitively of spaces are extensive. For instance, polyhedra and piecewise linear maps. Also, say, rational polyhedras and the corresponding restricted notion of map. They're all extensive. Pretty much any category that you think of as a category of spaces will be extensive. It is, although it doesn't look like it, it is quite powerful, the notion of extensivity. And for instance, as soon as you combine it with additivity, it collapses. So it's a genuinely opposite notion to that of additivity. If you have an extensive category, it's also additive, then it's trivial. Also, notice that the notion of extensivity doesn't require any limit, but if your extensive category happens to have finite products, then they distribute over coproducts. Also, the definition doesn't say anything about pullbacks, but pullbacks of complemented subobjects exist in any extensive category. Also, I should recall that many categories of spaces arise as opposites of algebraic ones. This is why I guess algebraic geometry exists. You have an algebraic category, you turn it around, and it is extensive. So you can think of it as a category of spaces. The category of rigs, the category of R algebras for any rig, the category of distributive lattices, the category of Boolean algebras, and the algebras, they all satisfy that if you turn them around, they are extensive. Now let's assume that our category, our extensive category, has finite products. Then we can say that an object X is decidable if the corresponding diagonal from X to X times X is complemented. We're going to put this name to the full subcategory of decidable objects. And it turns out that if your category is extensive and has finite limits, then the full subcategory of decidable objects is closed under finite limits, finite products, and subobjects, and therefore inherits extensivity from the original category C. Now, if you have accepted at least during this talk that an extensive category is a category of spaces, then I invite you to think of the full subcategory of decidable objects as the full subcategory of discrete spaces. For instance, every object in the category of sets is decidable. This is for a sort of an extreme reason. Every subobject is complemented. So in particular, diagonals are complemented. In the category of posets, an object is decidable if and only if it is discrete. Something similar happens in top. And the proof is, again, very similar. You choose a point, you take the product with the identity, you pull back the clopen diagonal, and you may conclude that the point is open too. So every point in a decidable topological space is open, and so it is discrete. These full subcategories that I mentioned earlier inherit this property, or the same proof works. And so, for instance, in compact Hausdorff spaces, an object is decidable if and only if it is discrete. But in this case, compactness plays a role, so it is the same thing as saying that it's finite. Something analogous happens in the category of stone spaces. And now let's move on to these sort of algebraic examples. Let's take a commutative ring K and consider the category of K algebras. As I said, if you turn it around, it is an extensive category. So let's picture an algebra A as an object in the opposite category. Well, it turns out to be decidable if and only if it is separable as an algebra in the classical sense. Right? Existence of this idempotent with special properties. If you look at it carefully, you'll see that the classical definition of separability in the commutative context really is just the opposite of the definition of decidable object. Let me emphasize this particular case, also a classical result. If you now take a field, not an arbitrary ring, but a field, and you consider the category of K algebras, then it turns out that an algebra is separable if and only if it is a finite product of very special K algebras, namely finite separable field extensions of the base field. So we'll come back to this later. Let's put ourselves then in an extensive category with finite products, and we're going to say that an object has decidable reflection if there exists a universal map towards the inclusion of decidable objects. Of course, you can always, for any functor, consider the objects that have a universal map towards a functor. But when you consider the special functor, the subcategory of objects with decidable reflection has a more geometric intuitive meaning. In fact, I'm going to invite you to think of it as being locally connected, roughly speaking, because we are going to think of the decidable reflection as the discrete space of pieces of X. And so the universal map intuitively sends a piece to the point where it lies. So space has decidable reflection if it has a discrete space of pieces. Right? That's the intuition, and it works. The full subcategory of spaces with decidable reflection, yes, is extensive. Of course, it contains the full subcategory of discrete spaces, meaning the decidable objects, as a reflective subcategory. This follows from generalities about the definition. What I should say here is that one would expect this to be closed under finite products, but I haven't managed to prove that. Although it happens in the examples, I don't know why it does, really. Now, as a concrete example, let me say that a topological space has decidable reflection if and only if it is weakly locally connected, in the sense that every point has a connected open neighborhood. This is slightly weaker than the standard notion of local connectedness. And I don't think it's very well known, but it is known. And I've found out that this subcategory of topological spaces is the smallest correflective subcategory of top that contains both locally connected spaces and connected spaces. So it's a fairly natural correflective subcategory of top. It turns out that in several examples, every object has a decidable reflection. In other words, the inclusion of decidable objects has a left adjoint, which moreover tends to preserve finite products. It's not always the case, but in the examples that are really geometric, it does preserve finite products because we know intuitively that if you take the product of two connected things, then the resulting product has to be connected. That's why pi zero should preserve finite products. Let's look at a concrete example. The category of finite posets. As I said already, the full subcategory of decidable objects coincides with the inclusion of the category of finite sets. And it does have a finite product preserving left adjoint, which sends a finite poset to the corresponding set of connected components or pieces. A different sort of example, so related but different, is the topos of simplicial sets. You know there's a canonical geometric morphism to the topos of sets, and it turns out that the inverse image of the canonical geometric morphism coincides with the full subcategory of decidable simplicial sets. And we know that the leftmost adjoint of this geometric morphism preserves finite products and assigns to a simplicial set the corresponding set of pieces. And in fact, this is a particular case of a very recent result that I got, and let me state it here for the first time in public. If you have a Boolean topos, then it happens that every hyperconnected essential geometric morphism from E to S, such that the leftmost adjoint preserves finite products, so you can think of it as a pi zero, then it turns out that the inverse image coincides with the full subcategory of decidable objects in E. And moreover, the geometric morphism is locally connected. So if you are into toposes, I thought this might interest you, but it's not going to be the main example. On the other hand, let's fix a field, and let's look at something more classical. We can consider the category of finitely presentable algebras, K algebras, and turn it around. As I said, this is an affine category, the category of affine K spaces. Very classical stuff. They didn't state it like this, but it is in the book by Demasure and Gabriel on algebraic groups. So it's really very classical stuff. The full subcategory of decidable affine K spaces has a finite product preserving left adjoint. So again, every affine scheme has decidable reflection. Now, in this position, it's fair to wonder what happens if we drop finite presentability. Of course, you know I'm interested in the induced topos, but for the sake of argument, let's consider the category of K algebras. All K algebras, not those that are finitely presentable. All of them. You turn it around, and you again have an extensive category with finite limits, so we can wonder about which these affine schemes in a more general sense have decidable reflection. And I don't have an answer to that, but by the end of the talk, you might be ready to conjecture an answer to this. What I want to speak is about NV algebras, which is maybe not familiar to everybody. If you never heard of them, maybe it is useful that I recall the fact that the category of NV algebras is equivalent to the category of lattice-ordered abelian groups with a strong unit. So in different clothes is again another very classical category. But let me introduce them in a somewhat non-standard way. Let's consider the finite dimensional cubes, and between them, the continuous functions for which there exists a finite family of affine polynomials with integer coefficients such that they patch up together to give you the original function f. Intuitively, these are continuous PL maps with integer coefficients, right? You won't be surprised that if we take all these finite dimensional cubes together and the magnoton functions between them, then you get an algebraic theory, and the corresponding category of algebras is the category of NB algebras. As I said, it's not usually presented this way, but if I do it this way, then you won't be surprised when I recall this theorem, which it's between inverted commas because I'm not going to recall all the definitions, but you see, we have finite dimensional cubes, affine linear map, piecewise affine linear maps between them, and so the category of finitely presentable algebras, OP, you won't be surprised, is a category of polyhedra and magnoton functions between them in a reasonable sense. So again, it is a very it's a category that looks very much like a category of spaces. But let me also give you the standard definition. This algebraic theory I introduced has a finite representation that you can get by extending the usual presentation for commutative monoids, say with addition and a zero, with an operation that looks like a negation and satisfies that double negation is the identity, that x plus 1 equals 1s, so you have an absorptive element, and this weird equation relating negation and addition. It's the same thing as what I said before. To give you a little bit more of intuition, it turns out that if you have a Boolean algebra and you consider this structure with joins, bottom, and negation, then you get an NB algebra. On the other hand, the typical NB algebra looks more like this. You take the interval, and as addition, you take the truncated addition. And for negation, you take 1 minus the argument. In fact, this NB algebra is so typical that an NB algebra, an arbitrary one, is simple if and only if it appears as a subalgebra of this unit interval, considered as an NB algebra, of course. So let's look at a couple of other subalgebras of the interval. Of course, you can intersect with the rational, and that gives you a rational NB algebra, which is quite smaller. At the other extreme, you have the initial algebra, which appears as a subalgebra of zero of the interval consisting of the endpoints. Also, for any n greater or equal than 2 natural number, you have a finite subalgebra of the interval. And as you may have guessed, the category of NB algebras is coextensive. And the proof is exactly as in the case of rings. You define what is an idempotent, and then you observe that idempotents in an NB algebra are in bijective correspondence with the product decompositions of the algebra. And then the proof works exactly as in the case of rings or Boolean algebras, exactly the same. But it's not exactly like rings, okay? So among NB algebras, monomorphisms are stable under push-out, which is not the case in rings. But anyway, they're very, very similar. And what we proved with Vincenzo is that an NB algebra is separable, meaning decidable as an object in the opposite category, if and only if it is a finite product of subalgebras of the rational interval as an NB algebra. So now let me put it together with the classical result I mentioned earlier. And let's consider a perfect field now, so we don't have to worry about inseparable extensions of base field? Well, with a perfect field, the classical result says that a K algebra is separable if and only if it is a finite product of finite extensions of K. Now you look at our result again, and you see that it's exactly the same, which leads one to wonder whether the following is a fair intuition, that the subalgebras of the rational interval are finite extensions of the base field 2, the initial object in the category of NB algebras. The results suggest that there's a possibility of a Galois theory of NB algebras, but one has to be careful because there are very few automorphisms going on around in the category of in simple NB algebras. Okay, so let's leave that for another moment, for another occasion. And rather than that, let's consider algebraic geometry in the context of NB algebras. Namely, we consider finitely presentable NB algebras. It is a coextensive category with finite colimits, so if we turn it around, we get an extensive category with finite limits. A good category of affine spaces. We can consider the inclusion of decidable objects, and again, it happens that every space has a decidable reflection. In other words, this inclusion of decidable affine NB schemes has a finite product preserving left adjoint pi 0. Well, as you can imagine, I'm looking at these things because I want to consider them as sites for toposes, okay? But I don't want to go into that direction. Rather, I'm going to give you a hint of the proof of this, which involves considering spaces with decidable reflection in a larger category. So in the larger category of NB algebras O. So let's say that an element in an NB algebra is a finite order, right? If the subalgebra it generates is finite. Right? That's a very natural algebraic thing that makes sense among NB algebras at least. Because if you take any NB algebra, it turns out that the subset of elements of finite order rank is a subalgebra of A. And moreover, the following items are equivalent. The first one is the class of objects that we want to characterize, namely the objects in the category of NB algebras that have decidable reflection as objects in the opposite of NB algebras. It turns out that those are exactly the ones such that the subalgebra R of A is separable, meaning decidable in the opposite category. And finally, these equivalent things turn out to be the same as those algebras that have finite product decomposition. So again, a space has decidable reflection if and only if it is a finite coproduct of very connected things. And in this case, the inclusion of the subalgebra of elements of finite order rank is in the opposite category, the universal map towards the space of pieces of the corresponding space. With that result, we then restrict it to the category of finitely presentable affine schemes, and that's what allows us to give a left adjoint. That's it. Thanks for your attention.
Let's thank Matías. Unmute or gesture. Okay, any questions or comments?
I'll ask you a quick question, Matías, because I didn't want to interrupt before, but in slide 6, I was having a hard time parsing the expression. You wrote a map from X to that one there. Is that like in the comma category or it's late? There were many talks.
Sorry, that one?
That one, yeah.
Well, you have a functor, and you consider an object in the codomain that has a universal map towards the functor. That's the general concepts. I'm restricting it to the very special case where the functor is the inclusion of the subcategory of decidable objects. There's maybe I'm confusing things with the notation. There's really nothing complicated here. It's a very basic general categorical
Sorry.
universal map.
What do you mean? Sorry. Oh, what do you mean by?
It's an object in the domain of the functor, together with the morphism from the given object towards the functor applied to the object in the domain, such that it's initial among those.
Okay, I think I see what I mean now.
So,
So
do
you're
you just? Yep. Sorry, go ahead.
X, you're thinking of X as a constant functor at C. Sorry, X is a constant functor from 1 to C.
Not really. No. I'm perhaps what it's confusing things is that, sorry, what's this? Is that I'm not giving a name to the inclusion. So the inclusion is tacit. And here the object, the decidable object, is called pi0 of C. It's an object, a decidable object. So it is in the subcategory. And then I consider it as an object. I include it into the larger category C. And I assume that there is a universal map there. Well, that's unexpected. Hold on, let me. Did I explain myself?
Yes, at least it's clear for me now. So thanks.
You have a functor B to C, a universal map from X to F is an object in its initial in that category, meaning it's an object B in the category B together with a map there that is initial in this category. Right? Yeah. Yes, I can only understand very simple things. So it has to be formulated in the most basic category theory possible. Otherwise, I just cannot get it.
This is nice.
Any other questions or comments? Okay, well, let's thank Matías again.
Thank you.
And that is the end of our session.
Yes, and I have made breakout rooms if people want to discuss any topics further with each other, then you can move yourself to a breakout room if you want to talk to people.
Okay. Well, thanks again.
And thank you. Let's thank all our speakers for today. Thank you so much for all your work.